Welcome back, everyone. In this lecture, we're going to discuss pooling layers, which is the last theoretical concept we need to cover before jumping in and coding out our own convolutional neural networks. Even with local connectivity occurring in these convolutional layers, when dealing with color images and possibly asking our network for tens or hundreds of filters, which is not uncommon, we still have a huge amount of parameters. We can use pooling layers to actually reduce this. Pooling layers accept convolutional layers as input. Here we see a very simple example of feeding in the direct input images to a convolutional layer, and then the result of the convolutional layer to the pooling layer. And as we just discussed, the convolutional layer has many filters, and then if we're dealing with color images, there's a filter per color channel. So we get very large tensors here in this convolutional layer. And even if there's still local connectivity to go from input to convolutional layer, we still have a lot of parameters. So as I mentioned, our convolutional layers will often have many filters. Here we just have a single filter being shown, but realistically we have many filters and then a filter per color channel, and we think of these as these large tensor objects. And what we want to do is reduce this. So let's just take a single filter and see how we would apply a pooling layer to the single filter. And eventually this will expand to many filters. Now there's different types of poolings, layers, and they use different subsampling or downsampling techniques, which is often what people also call pooling layers. They'll call them subsampling or downsampling layers. And you'll see why in just a second. So what we're going to do is reduce the size of this 4x4 filter using subsampling. So what we're going to do here is we're going to use the max pooling layer. And what we have to decide on is the window size and then the stride length or stride count. And what we're going to do is essentially very similar to the same way we apply an image kernel or image filter on top of an image, we apply this pooling window on top of this filter. So we have this 2x2 window, and we're going to, with a stride of 2, pass it along this filter and then grab the max values here. So this is max pooling. So out of 1, 3, 2, and 4, the max value is 4, and we continue with this. This is the max value of 9, and this 2x2, and in this 2x2 window, we get again max value of 9, and then over here on the bottom right, the max value is 3. And while we do lose some information in doing this, you can see that the general behavior has actually still been kept. The general information of the top left and bottom right is that those values, or along that diagonal, seem to be less than the diagonals going from bottom left to top right. So we actually still get to keep that information. Except now we're dealing with just 4 parameters instead of the previous 16 parameters. So we've greatly reduced the number of parameters here while still being able to keep the general information. With average pooling, you do the exact same process, except in this case, instead of taking the max value, you just average out those values. So you can tell that this would greatly reduce our number of parameters, which is why we feed in convolutional layers into pooling layers. This pooling layer will end up removing a lot of information, and even a small pooling kernel of 2x2 with a stride of 2 removes about 75% of the data that's inputted into it. However, hopefully those general trends will still be true throughout the pooling layer. Another really common technique to try to help out with the training time and overfitting problems a convolutional neural network could face is the dropout layer. Now, we've already talked a little bit about this, but dropout can be thought of as a form of regularization to prevent overfitting. And the way it works is during training, units are randomly dropped, which essentially just means you turn them off. And what you do is you provide a percentage somewhere between 0 and 1. You can say something like 0.5. And what that means is as you go through training, randomly 50% of those neurons in that layer are going to be turned off, so they don't overfit too much to the actual training data. So again, this helps and prevents units from co-adapting too much. Now there's also, I should point out, some really famous convolutional neural network architectures. There's LeNet5, AlexNet, GoogleNet or GoogleNet, ResNet, and you can check out the resource links to papers discussing these architectures. But what's really cool now is, given what you know about the theory behind convolutional neural networks, you can now take a look at these images that describe the actual convolutional networks and understand what's happening. They're essentially just different orderings of either a pooling layer or a convolutional layer or a densely fully connected layer, etc. It's just the size of them, what order they belong in, and that is the network itself. So you can see here an example of AlexNet, And you can also see here how they visualize the convolutional layers, and as you get further and further along the network, they begin to learn more complex patterns. And so here again is AlexNet, and you can see here we have max pooling layers along with some dense layers. There's also convolutional layers, etc. It's just the size and order and how many layers you decide to use that essentially makes up these famous architectures that you can easily look up online. Now keep in mind, convolutional neural networks can have all types of architectures. We showed the example of going from input to convolution to pooling layer, but it's also really common to feed convolutional layers into each other, into a pooling layer, etc. Or maybe you decide to go convolution pooling, and that works really well for your images. There's really no wrong way to run these experiments of what a convolutional neural network should look like. The best way to figure out what the best network for you is to just try different combinations and then use your metrics to decide which networks work better than others. Now, keep in mind, at the end of all these networks, you're going to have some sort of function that fully connects the results from the previous layer and then has an output layer which has the same number of neurons as the number of classes. So here we have probably the simplest convolutional neural network you can have, which is go from input to convolution to pooling to some sort of fully connected layer, which then leads to the output. Okay, so now that we learned about convolutional layers and pooling layers and the way these networks all work together, let's go ahead and finally code out our own convolutional neural network. I'll see you there.